Welcome to the Explainer. So let's jump right in, shall we? Today we're going on a totally hands-on journey to make one of history's absolute most famous math equations completely tangible. We are literally taking math off that dusty chalkboard and putting it right into your hands.
But first, I want you to think about this for a quick second. What on earth do ancient philosophers, origami, and a box of Cheez-Its actually have in common? I know, right? It sounds like the setup to a really weird joke. But stick with me because by the end of this explainer, you'll see exactly how these three wildly different things perfectly illustrate the exact same fundamental rule of the universe. Forget your standard math lesson. We're doing things differently today.
Here's our roadmap for today. 1. The most famous math formula. 2. Finding the missing side. 3. Proving it with Cheez-Its. 4. The Proofigami puzzle. And 5. The Wheel of Theodorus. All right, let's kick things off with section 1, the most famous math formula. You know, it's pretty wild, but ancient Egyptians actually discovered the 3-4-5 right-angled triangle way before the Greek philosopher Pythagoras came along and, well, slapped his own name on it. But to really grasp his theorem, we need a super solid anchor. So the most important word you're going to hear today is hypotenuse. Simply put, it's the longest side of a right-angled triangle, and you'll always find it sitting directly across from the right angle. Think about it like a giant puzzle. Every right-angled triangle has two shorter sides that meet to form that perfect 90-degree corner. We call these guys the legs, and we label them A and B. Then you've got the big one, the hypotenuse, which is always labeled C. Now, it doesn't really matter which of the shorter legs is A and which one is B, but C, that one is strictly VIP. It's exclusively reserved for that longest opposite side. And that brings us to the main event, the famous equation, a squared plus b squared equals c squared. So what does this all mean? Well, the crucial takeaway here is that in any right-angled triangle, if you square the longest side, it is exactly equal to the sum of the squares of the two shorter sides. It's just an incredibly elegant and honestly bulletproof rule of geometry. Moving right along to section 2, finding the missing side. Let's see how this actually works in real life when we need to find a missing length. We've got a fantastic breakdown from math teacher Mr. J in our source material. Imagine we have a triangle where leg A is 8 meters and leg B is 6 meters, and we need to find our hypotenuse, C. Okay, first step, square those legs. 8 squared is 64, and 6 squared is 36. Easy enough, right? Next, just add them together, 64 plus 36. And finally, because the formula gives us c squared, we just take the square root of that sum to completely isolate c. And boom, there's your aha moment. 64 plus 36 gives us exactly 100. And the square root of 100? That's 10. So our missing hypotenuse is exactly 10 meters. It's clean, it's super logical, and it works every single time you have a right triangle. But hey, seeing numbers on a screen is one thing. Actually feeling the math in the real world, that is a whole different ballgame. Which brings us to section 3, proving it with Cheez-Its. Oh yeah, we are pivoting straight from the chalkboard to the snack table for this one. It's a brilliant little exercise using just a standard right triangle and a box of Cheez-Its. Seriously. So you start by lining the perimeter of your triangle with whole crackers. Then you use those edge crackers to build perfect physical squares extending outward from each of the three sides. Basically, the length of the side tells you how big the square is going to be. So if a side is 3 crackers long, it becomes a perfect 3x3 cracker square. Now here is where the tactile magic actually happens. Once you've got squares built on all 3 sides, you take the crackers from the 2 smaller squares, the ones extending from legs A and B, and you literally stack them directly on top of the crackers that make up the big square for the hypotenuse C. And guess what? No way, they fit perfectly, exactly 1-to-1. The physical area of A squared plus the physical area of B squared literally equals the physical area of C squared. It is math you can eat. How cool is that? All right, time for section 4, the Proofigami puzzle. Now, if snacks aren't really your style, what about mashing up middle school geometry with the absolute beauty of Japanese paper folding? Yep, they call it Proofigami. Take a look at how specific segments on this square sheet of paper are really carefully labeled A and B right along the edges. You could actually measure these yourself to prove that all the segments labeled A are perfectly equal and all the segments labeled B are equal too. This little setup is the absolute foundation of our puzzle. So here's the jigsaw puzzle logic at play. You start with that flat, full square sheet of paper.
First, fold back 4 completely equal congruent triangles. By taking those 4 triangles out of the picture, the remaining area you can still see forms 2 smaller squares, one with an area of a squared and one with an area of b squared. Make sense? Okay, now unfold the paper entirely back to its original flat state. This time, I want you to fold back 4 completely different triangles. But, and this is key, they are the exact same size as the first 4. When you hide these 4 new triangles, the visible area that's left perfectly forms one single giant square with side lengths of c, meaning its area is c squared. Because you hid the exact same amount of paper both times, those remaining areas, they literally have to be equal. Boom! A squared plus b squared perfectly equals c squared. It's like a magic trick, but it's just pure math. Let's roll into section 5, the Wheel of Theodorus.
So we've done crackers, we've done origami paper, but this final, absolutely magnificent geometric spiral, it's actually named after Plato's own math tutor, a guy named Theodorus. The process here is super neat. You just use the corner of a basic 3x5 index card to give yourself perfect right angles, you draw a right triangle, calculate its hypotenuse, and then, here's the twist, you use that hypotenuse as the new leg of a brand new right triangle attached right to it. They all share this one common vertex smack in the center. As you keep repeating this, building hypotenuse upon hypotenuse, it creates this continuous, sweeping spiral. You can actually spiral outward exactly 16 times before the triangles even start to overlap.
And this perfectly sets the stage for what happens when hard mathematics and fluid art collaborate. Students in a California middle school actually created this stunning watercolor artwork using primary colors to mix secondary and tertiary colors right as the spiral rotated. It totally highlights the gorgeous visual pattern of those rotating triangles. Honestly, it just proves that math isn't just boring numbers on a page, it is structurally, undeniably beautiful. But check this out. Beneath all those pretty colors lies a brilliant mathematical pattern. If the starting legs of your very first triangle are 1 and 1, then thanks to our good friend the Pythagorean theorem, your first hypotenuse is the square root of 2. When you use that exact hypotenuse to build the next triangle, the new one becomes the square root of 3, then the square root of 4, then 5, and so on and so on. This entire spiral reveals this consistently growing pattern of irrational numbers, all stemming from that one single ancient equation, a squared plus b squared equals c squared. Mind-blowing, right? So from the ancient Egyptians to clever origami puzzles, all the way from boxes of Cheez-Its to breathtaking watercolor spirals, this one simple rule really does govern the geometric world around us. And that brings us to a final thought. Now that you know exactly how tangible this theorem really is, where else will you spot the hidden geometry of the Pythagorean theorem hiding in your daily life? Keep your eyes peeled for those right angles. Thank you so much for joining me on this explainer. Keep exploring, keep learning, and I'll catch you on the next one.